We present to your attention the research conducted by the scientists of the Pistrahach Institute for Applied Problems of Mechanics and Mathematics, National Academy of Science of Ukraine, on the following topic: spectral methods and nonlinear problems of heat and mass transfer. The problem of solving nonlinear thermal conductivity problems is relevant in many fields of science and technology due to the rapid development of technologies and the use of materials with temperature or coordinate-dependent characteristics, taking into account the history of the process. In such problems, the equations are nonlinear, and in case of complex heat transfer with the environment, the boundary conditions are also nonlinear. At the same time, many physical processes are described by dynamic systems, in which it is very important to take into account the history of the process. The problem of choosing the right mathematical models to describe the object under study is very relevant, as it will determine the reliability of the results obtained. One of the ways to take into account the effects of process memory is to use fractional order derivatives. The scope of the application is much wider than that of integral order differential equations, since the latter are their special case. Currently, the most commonly used are fractional order derivatives in Caputo terms, shown on the second slide. Most common areas of application are: first, research into mass transfer processes in complex natural structures. Second, research into blood flow processes in biological systems. Third, research into processes in epidemiology, finance, ecology, chemistry. A significant number of generalizations of different calculus are known in the literature. However, the application of fractional calculus in the mathematical modeling of physical processes is associated with a number of shortcomings in particular. First, the kernels of integral differential equations do not contain parameters of the environment and process under study. Second, the criteria for selecting the type of fractional derivatives and its order are unknown. Third, the methods used in the literature to solve applied problems do not always correspond to computational and technological constraints. A significant number of mathematical physics problems are solved by the method of separation of variables using certain orthogonal bases, in particular the classical orthogonal polynomials of Jacobi and Chebyshev-Laguerre. Therefore, the work establishes a connection between the fractional order derivative of Caputo and the aforementioned orthogonal polynomials. The following results are obtained. Theorem presented on this slide. It is known that in the basis of Laguerre polynomials, the integral convolution exactly transforms into the convolution of series. Let us assume that functions includes that in solution of the problem can be represented as a Fourier-Laguerre series. In this case, solving the boundary value problem using fractional derivatives reduces to solving an infinite triangular system of differential equations in coordinates. The application of fractional order derivatives to mathematical modeling of mass transfer in complex porous media confirms their effectiveness. The results obtained correspond to the qualitative picture of the process and maintain balance ratios regardless of the derivative or the parameter. The following mathematical model of heat and mass transfer using fractional order derivatives with respect to time are constructed in this work. Thermal conductivity model for conducting thermosensitive Hopf spaces shown on this slide. Here a three-component thermosensitive structure on the first figure is considered under the action of heat sources at the contact boundaries. Under described conditions, we determine the non-stationary temperature fields of the structural components from the heat conduction equations 1. Mathematical model of gas filtration in underground storage reservoirs shown on the fifth slide. The mass transfer process within the porous medium is analyzed by examining gas and fluid filtration, which can be described by an equation involving a fractional derivatives with respect to time. Equation 6. The density of extraction is determined by the formula that is presented on this slide. The reservoir pressure calculation algorithm was tested in the course of a computation experiment based on the data of the model PCG with the following parameter values presented on slide number 6. The input information was set by the values of pressure in control, metering and production wells, and by the values of volumetric gas extraction during gas extraction from the storage. Two cases are considered in the conducted experiments. In the first, a fractured environment is formed in the vicinity of the gas extraction zone in the OY direction, figure 2. In the second, a fractured environment is laid in the rear of the gas extraction zone in the direction of the OX, figure 3. For both such processes, particular Bx and By coefficient were used. In the context of superdiffusion, the distribution of permeability coefficient values play a crucial role. Treating it as a constant in the traditional approach leads to an imbalance in gas volume. To prevent such conflicts, the Grunwald scheme corrects the permeability coefficient in the geometric zones where significant difference in gas pressure exists and each iteration in FEM on the figures 4-5 show the distribution of gas pressure throughout underground gas storage. For the first experiment, figure 2 transverse fractures relative to the wellbore zone create superdiffusion along the OY axis to the coefficient By that was chosen in the range 1.1-1.7, while Bx remained unchanged. In contrast, in the other experiment, figure 4, superdiffusion occurs in the direction of the wellbore zone, which significantly affects the gas extraction regime and the pressure distribution in the reservoir. Figure 5. Conclusions. This work presents a mathematical model of diffusion taking into account the Caputo fractional derivative with respect to time. The choice of the fractional derivative with respect to time is explained by the fact that the diffusion process, like filtration processes, currently depends on the behavior of these processes in previous periods. Since the fractional derivative's parameter has a significant impact on the simulation results, the Laplace-Cartan integration transform is used extensively in the construction of the mathematical model of the diffusion process. This yields a solution and transformance which requires a transition to the original. An existing table of correspondence between originals and images, there are practically no formulas that allow the transition to the original based on the obtained image of solution using fractional derivatives. The use of the generalized F-Ross theorem is associated with significant computational difficulties and does not always allow obtaining a result that would satisfy the requirements for accuracy and technological limitations. Therefore, in this work, approximate and numerical methods are used to train. The use of fractional derivatives to study processes of different nature allows for a more adequate description of the studied processes. However, along with the positive aspects, there are a number of unresolved issues presented on the 9th slide. The first question is the question of choosing the type of fractional derivative for modeling the studied process remains open. Second, a practice shows mathematical models are sensitive to the order of the fractional derivative. However, the criterion for its selection is unknown. Third, currently, there are no sufficiently effective methods for solving boundary value problems using fractional order derivatives. Fourth, existing software packages for solving boundary value problems do not always give satisfactory results. This slide presents the list of references used in this research. Thank you for your attention. We wish you everyone health, peace, and significant scientific achievements.